Welcome back to the Deep Dive, Curious Learners. Get ready, because today we're talking about a scientific drama that has, well, it's pretty much upended what we thought we knew about heat.
We're talking about the material world. For decades, there's been one undisputed champion of thermal conductivity.
Diamond. The material that's best at getting rid of heat. It was always the benchmark.
Was.
Exactly. The king is dead. Long live the king. There's a new challenger called Boron Arsenide, or BAs.
And it has officially dethroned diamond. It's a stunning victory.
And this isn't just about, bragging rights in a lab. This is about completely reshaping how we build our electronics. It's about fixing the single biggest problem in modern tech.
Overheating.
Overheating.
It's this invisible problem, but it dictates everything. How fast your phone runs, how long its battery lasts.
And the energy a giant data center uses.
Exactly. So this deep dive is really our shortcut for you to understand why this one simple material could be the key to solving that huge, huge problem.
Our mission today is to pull apart the source material, unpack this story of skepticism, and finally, triumph.
And show how these ultra-pure crystals finally proved a theory right.
And look, if you appreciate getting this kind of knowledge delivered quickly, it really helps us out if you hit that like and subscribe button.
For sure. And we've got, affiliate links and some merch down below.
Right. Check that stuff out. And please absolutely suggest new topics for a deep dive in the comments. We do read them.
We do. So the history of boron arsenide it's just a fascinating story. It's a lesson in trusting your gut, even when everyone else is telling you to give up.
Okay, so let's start with the benchmark. Diamond. We need to give everyone some context here.
Right.
We measure this stuff in watts per meter per Kelvin, WMK. Diamond comes in at around 2,000 WMK.
And 2,000 that's an incredibly high number. Just for comparison, the copper in your electronics heat sinks. That's only around 400.
Wow, okay.
And silicon, the stuff that runs almost everything, is a really sluggish 150. So diamond is, 5 times better than copper?
That really puts its dominance in perspective. So why did scientists even start to look somewhere else? Why look at boron arsenide?
It all started back in 2013. A team at Boston College, led by David Boredo, they looked at the crystal structure of BAs and predicted, theoretically, that it could perform as well as diamond.
Or even better.
Or even better, yeah. Just based on models of how heat moves.
And how does heat move through a solid like this?
So in a solid material, heat isn't like a fluid flowing. It's all about lattice vibrations, which we call phonons.
Phonons, right.
The best way to picture it is like a set of interconnected springs and balls. That's your crystal structure.
Okay.
You heat one spot, a ball starts to vibrate, and that vibration just travels right across the whole structure.
So thermal conductivity is just how fast that vibration can get from one side to the other.
How fast and how efficiently, yeah. But then 4 years later, 2017, the scientific community hits this massive roadblock. This is where the physics gets really complicated. Revised models came out, and they introduced a new factor called four-phonon scattering.
Four-phonon scattering. That sounds incredibly specific. Why? Why was that suddenly the problem?
It's very technical, but basically a closer look suggested that at room temperature, it wasn't just 2 or 3 of these heat waves or phonons interacting.
It was 4.
It was 4 of them interacting all at once, and that creates a lot more friction, basically. It slows everything down.
And what did that do to the prediction for boron arsenide?
It completely slashed it. The new theoretical performance was down to about 13,360 WMK.
Oh, wow. So from potentially being better than diamond's 2,000 down to 13,360.
It was a huge disappointment.
So did people just give up on it?
A lot of people did. The consensus was, why bother with this difficult material if theory says it can't even come close to diamond?
And the early experiments seemed to prove that right.
They did. The first samples people managed to make were full of defects, and they only measured around 1,300 WMK.
So the experimental reality just seemed to confirm the disappointing new theory.
Exactly. The material looked like a bust.
Okay, but this is where it gets really interesting. Because the breakthrough team, this team at the University of Houston, led by Siwan Ren, they didn't accept that.
Right. They pushed back. Their core idea was brilliant because it was so simple.
Which was what?
They basically said, maybe the problem isn't the material's potential. Maybe the problem is just the samples we're testing.
The impurities.
The impurities, all the junk, the defects in the crystal, they thought of them not as tiny flaws, but as massive speed bumps for those phonons, for the heat.
So the challenge wasn't to invent something new, but to build a perfectly clean version of what they already had.
And that was a huge engineering challenge. They had to refine the raw arsenic, which is notoriously difficult to get pure, and just invent better ways to grow these crystals.
And their goal was to get them as close to perfect as possible.
Zero imperfections. They believed that purity would completely change the game.
And when they finally tested these hyper-clean crystals, they didn't just beat the old theoretical barrier.
They obliterated it. The headline result.
Yeah.
The high-purity boron arsenide samples showed a thermal conductivity above 2100 watts per meter per Kelvin.
Above 2100. So that's it. That is officially the end of diamond's reign.
It is. It beats the old experimental results, it beats the revised theory, and it beats diamond. It's the new gold standard.
This feels like a huge win for the experimentalists over the theorists.
It really is. It forces physicists to go back and look at those equations that led to the four-phonon scattering model. It just proves that purity wasn't a minor variable.
It was everything.
It was the entire key.
I love the quote from Professor Wren. He just said, "We trust our measurement, our data is correct, and that means the theory needs correction." That is a mic drop.
It absolutely is. It basically says that if you make the crystal lattice perfect, those heat waves can travel almost completely unimpeded. The speed bumps were just gone.
So let's get to so what is? This is great for the lab, but why does this matter to, you listening right now with a smartphone in your hand?
It all comes back to thermal management. Every single chip upgrade, every time we shrink transistors to make them faster, it generates more heat.
And right now, our devices have to slow themselves down to avoid, well, melting.
Yes. We are completely bottlenecked by our ability to get heat away from the processor.
Okay, but if this material needs such intense purification in a lab, how can this ever scale up? Are we just trading one problem for another, a manufacturing problem?
That's the key question, and that's where boron arsenide is so revolutionary. It's because of its dual advantage.
Dual advantage.
It's not just a great thermal conductor, it's also a really high-quality semiconductor.
Ah, okay. And usually material is good at one or the other, but not both.
Never both. Metals are great conductors, terrible semiconductors. Silicon is a good semiconductor, but, as we said, a terrible heat conductor.
So BAs breaks that trade-off.
It shatters it. The source material says it best. It has the best properties of a good semiconductor and a good thermal conductor that has never happened in other semiconducting materials.
Which means you could build the computer chip itself out of a material that is also its own perfect heat sink.
Exactly. You remove all those extra layers. Today you have the silicon chip, then some thermal paste, then a copper heat sink.
Maybe a fan on top of that.
Right. And each layer adds resistance. It makes it harder for the heat to escape. If the chip itself is made of a 2100 WNK conductor, you solve a huge part of the problem right there.
That would fundamentally change how we design everything.
Yeah.
And what about the practical side? I mean, diamond is also a great heat conductor. Why is BAs better?
Manufacturability, for one. Diamond requires extreme pressure and temperature to make. Boron arsenide is much, much easier and cheaper to synthesize.
So it's actually viable for mass production
Mm-hmm.
for things like data centers.
Right. And then compared to silicon, the current king, it's just a better performer.
How?
Well, a few reasons. It has what's called high carrier mobility, so electricity moves through it faster. It has a wide band gap, so it can handle higher voltages and temperatures.
So it's more robust.
Much more. And it has a thermal expansion coefficient that matches other materials well, which is important when you're building complex devices.
So they can run faster, use less energy, and tolerate harsher conditions.
Yeah.
I can see why the industry is excited.
The implications are just enormous for 5G, for space exploration.
And you know this is real because it's not just a research paper. There's big money and big industry behind this already.
Absolutely. This is part of a $2.8 million National Science Foundation project. It involves UC Santa Barbara, Notre Dame, UC Irvine.
A real consortium.
And critically, they have industrial support from Qorvo, which is a huge player in radio frequency tech. Industry's already planning how to use this stuff.
That's incredible. It's moving from theory to reality at warp speed.
Yeah.
Okay, let's wrap this up. What are the 3 essential takeaways you need to remember from all this?
Okay, number 1. Boron arsenide has officially beaten diamond. It hit over 2100 WMK, setting a new world record.
Second, the key to unlocking all that potential wasn't some new design. It was just extreme crystal purity. Getting rid of the defects proved the skeptics wrong.
And third, this material promises a cooling revolution because it has that super rare dual advantage. It's an amazing heat conductor and a high-quality semiconductor. That's the combo we've been waiting for.
So now you understand this fundamental shift that's happening, one that's going to affect every piece of tech you use.
And here's a final thought for you to chew on, something that builds on what Professor Wren did.
Okay.
If getting to perfect purity unlocked boron arsenide, what other materials are we underestimating right now just because our current samples are flawed or our theories are based on those flawed samples?
So the next big breakthrough might not be discovering something new. It might just be about finally perfecting something we already have.
It's possible, and the researchers are still working on VAs, trying to push that number even higher.
So stay tuned. The standard for cooling has been set, but it might still go up.
Thanks for diving deep with us.
We'll catch you on the next one.